the HPLC sample injector.
Okay, so at its absolute core, this is the injector's mission statement. It has to introduce a precise amount of your sample into that fast-moving, high-pressure liquid. But here's the key word, reproducible. It has to do it the exact same way every single time. If it doesn't, your data is basically useless. Reproducibility is everything. So injectors really come in two main flavors. You've got manual ones, where you're doing all the work by hand, and then you have automatic ones, which we usually just call auto-samplers. We're going to start with the old-school manual design because once you really get how it works, you'll see that an auto-sampler is just a clever robot doing the exact same thing.
The entire magic trick comes down to two valve positions, load and inject. In the load position, you're safely filling up a little holding area that's completely separate from all that pressure. Then, in the inject position, you just flip a switch that reroutes the flow to push that sample into the system. It's that simple.
Okay, let's look at step one, see how this works. In the load position, the high-pressure liquid, that's the mobile phase, it completely bypasses our sample loop. It's got its own path, going straight to the separation column. This creates a safe, totally pressure-free zone where we can use a regular old syringe to fill that loop with our sample. No pressure, no problem. And then, with just a simple turn of the handle, the internal pathways of the valve switch over. And bam! That's the inject position. Now look what happens. The high-pressure mobile phase gets rerouted. Instead of bypassing the loop, it flows directly through it, grabbing our entire sample and pushing it as one clean, tight band onto the column for analysis. It is just a brilliant and honestly a mechanically simple solution to a very tricky problem. The syringe measurement method, you intentionally underfill the loop. The rule of thumb is to inject less than half the loop's total volume. Why? Well, this makes sure that the precise amount you carefully measured in your syringe is exactly what goes into the middle of the loop without any of it getting lost or smeared out near the ends. Here, the syringe is the hero.
But if you want to use the loop measurement method, you do the complete opposite. You massively overfill it. We're talking injecting at least 3 times the loop's volume. Now that might sound wasteful, but there's a good reason. You do it to be absolutely positive that you've flushed out every last trace of old solvent and completely filled the entire loop with your new sample. This way, the loop's fixed volume becomes your measurement, which can be incredibly reproducible.
What is an autosampler? It's basically a sophisticated robotic arm and valve system that does exactly what we just learned how to do by hand. It'll pick up a sample vial, draw up the liquid, move to the injection port, and then perform that same load and inject sequence over and over and over again for hundreds of samples without you ever having to touch it.
A lot of autosamplers use what's called the pressure injection method. And if you look at the diagram here, it should look really familiar. Yep, it's the same exact principle as the manual injector we just talked about, with a sample loop that gets switched between the load and inject positions. It's just fully automated for speed and ultimate precision.
But there's another common design called the total volume injection method. Now you can think of this one as kind of skipping the sample loop part. A super high precision pump acts like a perfect syringe, and it sucks an exact volume directly from the sample vial. Then it injects that entire measured amount straight into the system. The big upside here is flexibility. You can program pretty much any injection volume you want without ever changing out the hardware.
You know, in the incredibly complex world of high-performance liquid chromatography, or HPLC, there's one component that's quietly doing all the heavy lifting. Today, we're going to pull back the curtain on the pump, the true beating heart of the entire system. So what makes this thing tick? Let's dive in.
At its most basic, the pump's whole purpose is to shove a liquid, what we call the mobile phase, through the entire system. But it's not just about brute force. Here's the real kicker. It's all about control. It has to deliver that liquid at a very specific, incredibly stable flow rate. Because in the world of HPLC, precision isn't just a nice to have, well, it's everything. So we know the pump moves liquid, but what is that liquid exactly? Does its makeup stay the same, or does it change? This brings us to the two fundamental ways a pump can operate, which we call elution modes.
So you've got two main flavors here. On one side, you have isocratic elution. This is kind of the set it and forget it approach. The solvent mix you start with is the same mix you end with. Simple. But then you've got its polar opposite, gradient elution. This is where the pump has to work much harder, actively mixing different solvents to change the composition over time. It's way more powerful, but it puts a huge demand on the pump's precision.
Basically, they fall into 3 main camps. You've got your reciprocation pumps. These are the ones you'll see most often. Then there are displacement pumps, which you can kind of think of them like a super precise, powerful syringe. And finally, you have pneumatic pumps, which use gas pressure to push the liquid.
there, the plunger pump. It's a type of reciprocation pump, and honestly, it's the workhorse of the industry. If you understand this one, you've pretty much got the core concept down for most modern systems.
Okay, so what are the key parts inside? First, you've got a motor that turns a cam. That's what drives the whole thing. That pushes a plunger back and forth inside this little sealed-off chamber called the pump head. And the real heroes here are the check valves. Think of them as tiny one-way doors that make sure the liquid only goes in the direction we want it to.
First, the plunger pulls back, creating a little vacuum. Whoosh! The inlet valve opens and sucks the mobile phase in. Then, the plunger shoves forward. Bam! The pressure skyrockets. The inlet valve slams shut and the outlet valve is forced open, pushing a tiny, precise pulse of liquid out into the system. And it just does this over and over and over again, creating that powerful, high-pressure flow. That reciprocation pump, yeah, it gives you awesome high pressure and it's great for mixing those gradients. But, and this is a big but, that push-pull action creates tiny pulses in the flow. That can create what we call baseline noise, this wavy signal that can totally hide what you're trying to see. Now the displacement pump, its flow is smooth as silk, absolutely no pulses. The downside? It's like having a tiny gas tank. It runs out of solvent fast, and it's a pain to refill. And finally, the pneumatic pump. It's cheap and pulse-free, but it's just not very powerful. It can't handle high pressures, and you can forget about doing gradient dilution.
The guard column.
So what the heck is a guard column? You can think of it like a bouncer at a club, or maybe a really high-tech coffee filter. Its entire purpose in life, its one job, is to grab all the gunk, all the nasty impurities from the liquid, and stop them in their tracks. It makes sure nothing gets through that could mess up the really important stuff downstream.
And check out where it sits in the system. This diagram shows it perfectly. See that? It's wedged right between where the sample gets injected and the main column. It's the ultimate first line of defense, making absolutely sure that only the clean, pure sample gets to move on.
The analytical column.
The column is jam-packed with these unbelievably tiny particles, usually silica gel. And when I say tiny, I mean it. We're talking 5 to 10 microns. That's smaller than one of your red blood cells. So as the chemical mixture is pushed through this super dense maze, it's kind of like a race with a bunch of obstacles. Some molecules are fast, they zip right through. Others get stuck on the obstacles for a little while. And because they all move at different speeds, they pop out the other end one by one, perfectly separated.
On the left, that's our bodyguard, the guard column. And next to it, those long, thin ones, those are the analytical columns, the race tracks where all the high-precision work happens. First up, rinsing. It's absolutely key. After you run a sample, you've got to wash out anything that's left clinging to the inside. You use a special rinsing liquid, the fancy word is eluent, that's really good at flushing things out. But what you use depends on the job you just did. If you were running in reversed phase mode, which is for separating molecules that don't like water, you'll use a rinse with a lot of organic solvent. But if you were using ion exchange to separate things by their electrical charge, you'll use a high-salt solution. It's simple, really. You've got to match the cleaning solution to the type of mess you're cleaning up. Remember this, never, ever let the inside of that column dry out. I'm serious. If that packing material dries, it can shrink and crack, creating these little rivers or channels inside. And just like that, its ability to separate anything is gone. Poof, the column is toast. Permanently ruined. It's the one mistake you just can't make.